As you remember, many data are symmetric and they're bell-shaped. For instance, the distribution of men's and women's heights in the United States are symmetric and bell-shaped. Basically, you are allowed to use the empirical rule to do a little bit of calculations. What does it tell us? It tells us for data that are distributed approximately and they have bell-shaped graph, then 68% of the data lie within one standard deviations of the mean. So this is what you see here. This is the shaded area, shaded graph. 68% of the data are within one standard deviations of the mean. Here you have the mean of the data and one standard deviation to the left, x bar minus s, and one standard deviation to the right, x bar plus s. Then about 95% of the data lie within two standard deviations of the mean. You're basically having this scenario, two standard deviations away from the mean. It counts 95% of the data. And finally, 99.7% of the data lie within three standard deviations of the mean. Here we go. So 3 standard deviations away from the mean, x bar plus 3s and x bar minus 3s. This is empirical rule. Help us to do a little bit of calculations. For example, in a survey conducted by National Center for Health Statistics, the sample mean height of women in the United States was 64.2 inches. The sample standard deviation is 2.9 inches. Estimate the percent of women whose height are between 58.4 and 64.2 inches. This is the distribution that we have. As you can see, it is symmetric and bell-shaped. So you're allowed to use the empirical rule. The mean or the balancing point, which is located in the middle, is 64.2. One standard deviation away from the mean are located here. 2 standard deviations away from the mean and 3 standard deviations away from the mean. But take a look. The mean is 64.2. One standard deviation to the left is 61.3, and one standard deviation to the right is 67.1. 2 standard deviations to the left is 58.4, and 2 standard deviations to the right is 70, and so on. Very good. So let us do the calculation. Because the distribution is bell-shaped, you're allowed to use the empirical rule. The mean height is 64.2. So when you're subtracting 2 standard deviations from the mean height, what you get x bar minus 2s, which is 64.2, which is the mean of the data that you have, minus 2 times standard deviation, which is 2.9 given in the question to us. If you do the algebra, it is 58.4. But based off of the empirical rule, the percentage below the graph between 58.4 and 64.2 is going to be this area here. The probability, the area. So what are you going to do? You're going to add this little area, which is 13.5% plus 34%. Here we go. If you add them together, you get 47.5%. What's the meaning of that? It means that about 47.5% of women are between 58.4 inches and 64.2 inches tall. Now the question is, what if you don't have a nice distribution like this? In that case, if the empirical rule doesn't apply, we're going to move on and use an inequality, Chebyshev inequality. Chebyshev theorem says the portion of any data set lying within K standard deviation of the mean is at least 1 minus 1 over K squared. If K is equal to 2, in any data set, at least 1 minus 1/4, 3/4, or 75% of the data lie within 2 standard deviations of the mean. When K is 3, in any data set, at least 1 minus 1 over 9, or 8 over 9, or if you do the division, 88.9% of the data lie within 3 standard deviations of the mean. Okay, let's take a look at one example together. The age distribution for New York and Alaska are shown in histograms below. Apply Chebyshev theorem to the data for New York using K equals to 2. So as you can see, these two data sets are not normally distributed. The mean of the population and standard deviation of population for New York and Alaska are approximately given to us. Let us apply the theorem. The histogram on the left-hand side shows New York's age distribution, moving 2 standard deviations. To the left, why 2? Because K is equal to 2. Mu minus 2 standard deviation is approximately 38.8 minus 2 times 22.5, which is negative 6.2. So moving 2 standard deviations to the right of the mean, we get mu plus 2 sigma, which is 38.8 plus 2 times 22.5, which is 83.8. By Chebyshev theorem, you can say that at least, so the wording is at least here, versus what you learned in empirical rule. Here you have at least 75% of the population of New York is between 0 to 83.8 years old. 0, it means that they are newborn, and 83.8 years old. So that's the use of Chebyshev's theorem. In general,